Hello dear, good morning and welcome back. So you have started watching a video on support vector machine, and we are going to discuss today the kernel method. Okay, but before that I would like to just recap a few issues which were raised by some of you during discussion forum, that how regularization works. So this is very simple, that when there are outliers, that means what is outlier? Means your data is noisy. Okay, uh, whoever was not supposed to be somewhere, they are there. So this is called noisy data. So if you have noisy data, then of course we have added a term called regularizer. Okay, so C is a parameter, okay, and xi I is another parameter which is measuring the distance of the outlier. Okay, this should have been here, but now it is here. This should have been here, but it has stepped out. Okay, these are called outlier. So if you see, you can analyze, right? So we have kept this term in the objective function itself, and then we have kept it in the constraint, and then we have optimized it so that the outlier against outlier, the support vector machine, the decision boundary to some extent will be most optimal. Okay. Now try to look here. What value of C we should select? That depends on the kind of data. For example, if data is not noisy, okay, means you have perfect gutter, okay, and decision boundary will be perfect. So this will be near about 0. Okay, but if you have noisy data, that means if outliers are there, C will be increased. Say it could be 1000, 2000, 3000. Okay, so more outliers, and what effect actually it will have? It will have the effect of shrinking the width of the gutter. Okay, because it will try to just make it in make a decision boundary in such a way that this outlier will be considered in the negative class. Likewise here also. So in that process, it will try to shrink, okay, the width of the gutter. Okay, so this is the intuitive description of what the regularizer is doing. So, and as you know, support vector machine is not very good against noisy data. The reason is this. Okay, so noisy data means you have outliers, and the width of the gutter will be shrinking, and in that case, support vector machine will lose its speciality. That is, it will be just like any other. Okay, if you have data like this, okay, so it will try to just the width of the gutter will be shrinked in such a way that it will reduce to a normal classifier with other tools like logistic regression and all. So anyway, the take home is that if you have noisy data, then C will be large. If you do not have noisy data, C will be small, and the effect of noisy data is that your gutter width will be shrinking, will be narrowed down. Okay. So this is what I wanted to communicate. Okay, now today we are going to discuss a very interesting and very important issue, as you know, that how, because support vector is elegant, it has quadratic optimization theory in the background, and it is very capable of making maximum margin design maximum margin classifier. But as you have seen, this is the model so far we have developed is only making support vector machine capable of classifying linearly separable samples. Okay, but what if we have a non-linearly separable problem like this? Okay, then can we extend the beauty of support vector machine? The answer is yes, we are trying to do that. And in this context, you see, we will discuss many important issues. Here is a visual, these are your one class, say a negative class, okay, say these are negative class and these are, say, your positive class. So definitely in this 2D, they are not separable. Then the idea is, can we go to a higher dimensional feature space? Here it is 2D, okay, and project the data in the higher dimensional feature space by somehow finding a mapping function called phi, which will operate on this lower dimensional samples, and it will take to the higher dimensional space. And can it solve our problem? Okay, so this is the picture which is trying to show you. You can see that yes, now in that higher dimensional feature space, it looks that two samples are linearly separable, and once we could reach to that higher dimensional feature space, then in our because now x in the higher dimensional feature space has become phi x. Actually, we are using this terminology, x I, same as so far whatever we have discussed, sample, okay, and these are actually samples, okay. So don't be confused if you see this kind of notation. Sorry about that, but these notations are, this is samples from the positive class, this is samples from the negative class, and we have actually used this sample, this notation for support vector, where there is no plus or minus. This is support vector. Okay, that is what the terminology we have used. So don't be, they are same actually. Okay, and later on we will also see, we will use a terminology like, okay, this and xj, okay, is same as x z vector. Okay, so xj we can find. Now let us concentrate what we have shown you here pictorially, how intuitively we can establish that, and then we will talk about mathematics and all. You see, we have actually in reality, we have two kind of dimension, higher dimension, lower dimension. What does it mean? You see, you already know, this is the most basic thing. This is a point. So there are concept, very important concept. Physical dimension, suppose physical dimension, what does it mean? Suppose we know physically point doesn't require any dimension, so it is 0 dimension. Then line, 1 dimension. Then area, you have 2 dimension, and then this is having 3 dimension. So these are called physical dimension. Okay, and without abstraction, we can conceptualize 4 dimension, right? Say a car, which is a 3D object, okay, is actually moving with a speed, okay, is moving, okay. So it's a 3D object. With respect to time, it is changing its position, orientation, etc. So we can visualize with our eyes up to that. So these are physical dimension. But there are another kind of dimension which we are interested in, and I would like you to know the difference between them. That is called representational. I am calling them representational dimension. Representational dimension. Here you see, say I would like to represent point in 1D, okay. So my point can be here, okay, and say if this is my beginning, this is my zero line, okay, and my point is at a distance, say 2 millimeter, okay. So I need this dimension to fix, to understand where my point is, okay. So in one dimension, the point which earlier has physical 0 dimension will have 1 dimension now. Same point, if I want to represent it in, say, two-dimensional feature space point, which physical dimension, which doesn't have any physical dimension, but it requires 2 dimension, isn't it? x1, x2, okay. So it will have 2 dimension. We also got this belongs to, okay. So it requires 2 coordinates, x1, x1, x2, x1, x2. Same point in another, if I increase the dimension now, say x1, x2, x3, same point will have now 3 dimension. 3 for representation, same point for representation, I need 3 parameters, okay. So now it belongs to 3D. So this is actually representational dimension. So when we talk about infinitely large dimension, how you can how this is a kind of abstraction. There is kind of representational dimension. Let us we'll come back here and let us look. You see, say I have a small picture of 64 cross 64 dimension. Okay, these are actually 64 what? The pixel intensity values is a matrix, and each element represents the pixel intensity value of this picture, and it is RGB, 3 channel it has. So what will be the dimension if I like to represent this picture in the form of a vector? So what will be the dimension of the vector? It will be having a huge dimension, right? 1, 2, 2, 8, 8 cross 1 dimension vector. If I have a bigger image, 1000 cross 1000, okay, size and 3 channel with 3 channel, I will have a vector to represent this. I require a 3 million cross 1 vector, okay. So these are called representational dimension. Higher dimension, lower dimension. In this context, you should understand that they are basically abstraction beyond 4th dimension. We cannot, although physically do not conceive, but they exist for our mathematical computation, and why they exist, how they exist now, perhaps you know a little bit about it. Now with this background, let us try to see what difference it makes when we try to visualize something in a lower dimension and something in the higher dimension. Okay, I will try to give you an example. Say I have sorry about that. So I have few in in the in this dimension, in x dimension, I have some samples, these and these, they are jumbled up. But this is in one dimension when I see from here. Okay. But what if I try to project some this samples in higher dimension with some mapping function, say, okay, I am not changing the color for a want of time. You see, what in this first one dimension seems to be jumbled up, okay, and then you need to have a decision boundary which is very peculiar, separate like this. But if you go to the 2D, they are completely linearly separable, and you project the data, they are complete. And you see, again, project back in the first dimension, in the one dimension, they will be again jumbled up. So intuitively, if you move to higher dimension, then the samples which otherwise is not linearly separable will attain that linear separability. Okay. More examples I can give. You see, this experiment you can do at home. So you have a table, and you have a book, you have some other items here, and you are seeing in 2D, keeping your eyes here. Okay. Okay. And you will see there is these three items are not separable at all. There is no conceivable decision boundary which can separate these two. But the moment you just try to see from here, and clearly you see they are linearly separable. There is a decision boundary. So what I am trying to make a point here, that if you go to the higher dimension, then the samples can be actually linearly separable. That's very important. And in support vector machine kernel method, it can be proved that you can, if samples are not linearly separable in one dimension, two dimension, three dimension, four dimension, then you can even extend it to infinitely large dimensional feature space, where ultimately the samples will be linearly separable. Okay. So now you understand what kind of dimension we are talking of. Those are not physical dimensions necessarily. And again, I can give you some examples. Say I have XOR like situation. My samples are like this. Okay. Okay, and clearly they are not separable by a linear decision boundary. Okay, they cannot be linearly separable, and support vector machine as such will fail to separate, because inherently it is a linear machine. But what we will do, we will try to figure out a mapping function which we can call phi x here, which will operate on x is a vector, x1, x2, all these samples having x1, x2 dimensions. It will operate on that, and it will project. You see, x1, x2 plane, this samples remains there, but I have only projected these samples on the 3 dimension, and clearly in 3 dimension there is a plane which can separate these two classes. So even though it is binary classifier, even though it is only linear classifier, you see, only thing I will have to apply support vector machine's principle in a higher dimensional feature space. Okay. Another example. So this is highly not linear. It's not separable in 2D, but again, I am projecting, designing a mapping function phi, and then you can just imagine a plane, separating plane now, which can actually classify between these two classes. Okay. So I think now the take home here is that support vector machine can be used in a higher dimensional feature space as a linear classifier, but eventually in higher dimensional feature space, what it is classifying in a given lower dimensional feature space, it was nonlinearly separable problem. So nonlinearly separable problem can be separated using higher dimensional feature space. Okay. So we are going to discuss now, fasten your seatbelt, and next class we will discuss what the kernel method is and how actually the support vector machine can perform in a higher dimensional feature space. Till then, thank you for your attention. Stay safe. Goodbye.